Hello everyone and welcome to my channel. This is the A Tutor. Today we're going over dividing polynomials. And there are two ways to divide polynomials. You can use long division or synthetic division. Let's start with long division. Before we jump into using long division to divide two polynomials, let's first remember how to use long division to divide two numbers. Say we have 729 divided by 3. Write your divisor on the outside, which is our 3, your dividend inside our long division symbol, that's 729, and let's divide going digit by digit from left to right. 3 goes into 7 2 times, so we write that 2 up top. 3 times 2 is 6, subtract down and we get 1, bring down the 12. 3 goes into 12 4 times, 3 times 4 is 12, subtract that down and we get 0, bring down the 9. 3 goes into 9 3 times, 3 times 3 is 9, subtract that down and we get 0. So our answer is 243. Say we have 176 divided by 5. Same thing, take your divisor, which is 5, put that on the outside. 176, which is the dividend, goes inside our long division symbol. 5 does not go into 1, but it does go into 17 3 times. So 5 times 3 is 15. 17 minus 15 is 2. Bring down the 6. 5 goes into 26 5 times. 5 times 5 is 25. Subtract down and we are left with 1. So in this case, our remainder is 1. And 176 divided by 5 is equal to 35 1/5. Whenever we have a remainder, we put that remainder over our divisor as a fraction. Now, let's look at an example using polynomials. We have k squared minus 7k plus 10 divided by k minus 1. K minus 1 is our divisor, so that goes on the outside of our long division symbol. And k squared minus 7k plus 10 is our dividend, which goes on the inside. First, we need to see how many times k goes into k squared. Or you can think of it as what times k will give us k squared. In this case, all we need to multiply k by is another k. Now when we're starting to write our quotient, or the answer to this expression, we need to line up our like terms. Since all we're multiplying is a k term, this k is going to go above the minus 7k within our polynomial. Now, we multiply k by our k minus 1, just like we did in our other example using our numbers. So k times k is k squared, and k times negative 1 is minus k. We're subtracting this expression. So when we subtract, we can change all of our signs and add down. If you'd like to go over adding and subtracting polynomials, please check out my video on adding and subtracting polynomials linked below. Now we'll simply add down. Our k squares cancel out, and negative 7k plus k is negative 6k. Let's bring down the plus 10. Now we have negative 6k plus 10. K goes into negative 6k negative 6 times. So we'll write negative 6 above our plus 10, those are our like terms, and we'll multiply negative 6 times k minus 1. So we get negative 6k plus 6. Change all of our signs and add down. This leaves us with 4 as our remainder. We have to put that remainder over our divisor, so our final answer becomes k minus 6 plus 4 over k minus 1. Let's look at another example. We have n squared plus 10n plus 18 divided by n plus 5. Let's write this in long division form. So n goes into n squared n times, or n times n gives us n squared. So we'll multiply n by our divisor, and we get n squared plus 5n. We're subtracting this, so let's change all of our signs and add down. We're left with 5n. Let's bring down the 18. N goes into 5n 5 times, or n times 5 gives us 5n. We'll multiply 5 by our n plus 5, subtract down, or change all of our signs and add, and we're left with negative 7. This is our remainder. And our final answer becomes n plus 5 minus 7 over n plus 5. Now, say we have 2x squared minus 17x minus 38 divided by 2x plus 3. Let's set up our long division. 2x goes into 2x squared x times, or 2x times x gives us 2x squared. So now we'll subtract 2x squared plus 3x. Change our signs, add down, and that leaves us with negative 20x. Bring down the negative 38. 2x goes into negative 20x negative 10 times, or 2x times negative 10 gives us negative 20. So we'll subtract negative 20x minus 30, change all of our signs, add down, and our remainder is negative 8. So our final answer is x minus 10 minus 8 over 2x plus 3. As I mentioned earlier, there were two ways to divide polynomials. One was using long division, and now let's look at dividing polynomials using synthetic division. When we use synthetic division, we use the coefficients of our polynomial to find our quotient. Let's use the first example that we used. That was k squared minus 7k plus 10 divided by k minus 1. So here was the process when we used long division. Now let's use synthetic division. First thing we want to do is rewrite our divisor and our dividend so that we can identify the components we need to do synthetic division. We'll take our divisor, k minus 1, and set that equal to 0 and solve for k. Then we'll look at our dividend and find the coefficients of each term. In this case, our k is equal to 1, and our coefficients are 1, negative 7, and 10. So let's set up our synthetic division. First, we'll write our 1 and section it off. Then, in a line, we'll write our coefficients from our polynomial. The pattern for synthetic division is multiply, add down, and repeat. So we're going to start by bringing down our first coefficient in this polynomial, the 1. So the 1 comes all the way down. We're going to multiply 1 by our divisor, which in this case is 1. So we get 1. 1 times 1 is 1. And then we'll add down. Negative 7 plus 1 is negative 6. We'll multiply negative 6 by 1. We get negative 6. And add down. 10 plus negative 6 is 4. 4 is our remainder. Now we found the coefficients of our quotient. Basically, we found the coefficients to the answer of this expression. We need to put our variables back into our quotient, and when we do this, we're going to start with 1 degree less than what our original polynomial was. Our original polynomial was degree 2, or k squared, so we're going to start with k to the first power. Our first coefficient will have a variable with k to the first power. Our second will be k to the 0, or just 1. And 4 is our remainder. So if we put our variable back in, we get our final answer as 1k, or just k, minus 6 plus 4 over k minus 1. And looking back at the answer that we got the first time, we know that we're correct. So remember, the pattern for using synthetic division is finding all your coefficients, multiply, add down, and repeat. Let's look at another example. We have n to the third plus 7n squared plus 14n plus 3 divided by n plus 2. We'll start by rewriting our divisor and our polynomial. Set that n plus 2 equal to 0 and find n equals negative 2. Next, let's identify the coefficients of each term within our polynomial. We have 1, 7, 14, and 3. So let's set up our synthetic division. We'll write negative 2 by itself, and the rest of the coefficients in line going across. Bring the first coefficient, bring that 1 down. Remember, our pattern is multiply, add down, and repeat. So we'll multiply 1 by negative 2. We'll add 7 and negative 2 and get 5. And we repeat. 5 times negative 2 is negative 10. 14 plus negative 10 is 4. And 4 times negative 2 is negative 8. 3 plus negative 8 is negative 5. Negative 5 is our remainder. The degree of our original polynomial was 3, so that means we're going to start with 2 as our degree for each of our terms. We get n squared, n to the first, and n to the 0. And our final answer becomes n squared plus 5n plus 4 minus 5 over n plus 2. As we've seen, when we're dividing polynomials, we may have a remainder. The remainder theorem tells us what the remainder of our polynomial will be, and it helps us check to make sure that our division is correct. The remainder theorem states, for p of x divided by x minus a, p of a equals r. P of x is our polynomial, x minus a is our divisor, p of a is just plugging in a for x, and r is the remainder of p of x divided by x minus a. Let's look at this theorem in action, going back to our first example again. As we know, k squared minus 7k plus 10 divided by k minus 1 is equal to k plus 6 plus 4 over k minus 1. If we use the remainder theorem, we should get 4 as our remainder. So our p of x, or in this case p of k, is equal to k squared minus 7k plus 10. And for our a term, since our divisor is k minus 1, that means a is equal to 1. So let's plug in 1 for k. P of 1 is equal to 1 squared minus 7 times 1 plus 10. After simplifying, we get 4. This was our remainder, so we know that our division was correct, and we verified our remainder of this expression. Let's take another example using synthetic division. We have 3x to the 7th minus x to the 4th plus 2x to the 3rd minus 5x squared minus 4 divided by x minus 2. Let's rewrite our expressions. So we have x minus 2 and our polynomial. Notice that we don't have every exponent represented in this polynomial. As we go through, we see x to the 6th and x to the 5th are missing, so we have to add those in. We must represent every single term within this polynomial, including 0 terms. So that means when we expand our polynomial to find our coefficients, we have 3x to the 7th plus 0x to the 6th plus 0x to the 5th minus x to the 4th plus 2x to the 3rd minus 5x squared plus 0x minus 4. Now we can identify all of our coefficients. Let's set up our synthetic division. We follow the pattern, multiply and add down, multiply and add down. This gives us a remainder of 360. Our variables will start with x to the 6th power and go all the way down to x to the 0. So our final answer becomes 3x to the 6th plus 6x to the 5th plus 12x to the 4th plus 23x to the 3rd plus 48x squared plus 91x plus 182 plus 360 over x minus 2. Let's use the remainder theorem to verify our remainder. Our a, in this case, would be 2. So let's plug in 2 for x. Solving this gives us 360, which is exactly what we're looking for, and we know that we have the correct remainder and therefore the correct quotient. Thank you so much for watching. I hope you enjoyed. Please comment down below what other topics you'd like for me to cover. See you next time.